everyone, and welcome to the Metallurgy stream of IChemE's second day of the Student Summit. So before we start, I'd just like to acknowledge the traditional owners of the country throughout Australia and recognise their continuing traditions throughout, continuing connections to the land, waters and the culture. We pay our respects to their elders past, present and emerging. So if you don't know what metallurgy is and you decided to attend anyway, I like your attitude. Metallurgy is the field concerned with the properties of metals and their purification. So essentially how you turn rocks in the ground into metals, which are so important in our lives right now. So today's sessions will involve talks from Janine Herzig, Vagenas and Leon Prentice, and then a panel involving all three. We have some amazing speakers today, and I'm sure that everyone here will leave this session with at least one important note. For some housekeeping, please, if you have any questions, send them into the Q&A section in the chat, and I'll make sure to ask as many as I can during the panel, and our host will be sure to answer them. So for now, I'm just going to pass it over to Thomas so he can introduce the speakers.
Thanks, Jack. Up first today, we have Janine, who has almost 30 years of experience in the resources sector and has been involved in projects across all stages, from due diligence to feasibility and production. Currently, she is the Australasian Institute of Mining and Metallurgy's president and chair of board, and we're here to have her speaking about the many pathways in metallurgy and her professional journey from chemical engineer. Thank you.
Thanks very much for that, Thomas. It's wonderful to be here with you all today. I hope you're all keeping well, staying safe. I could probably spend 20 minutes talking about the impact of the current pandemic on the minerals industry, but we're not here to talk about that today. So really, I hope that I can inspire you, if you have not considered a career in metallurgy and in the resources sector, that I can actually inspire you to have a look into that, because it's a terrific industry to be part of. So as Thomas mentioned, I'm the president of the IChemE, the Australasian Institute of Mining and Metallurgy, which is the professional body, peak body for minerals professionals and multidisciplinary, so similar to IChemE, but we actually welcome all disciplines from the mineral sector, and that can be everything from metallurgists to geologists, mining engineers, social performance practitioners, environmentalists, law, you name it. Anyone involved in resources can find a home with IChemE. So I've been part of the IChemE for 30 years, so pretty ingrained into me. And I'll talk a little bit about the importance of becoming a member and being part of a professional association as well. I also run a consulting business, Metval Consulting, which is basically doing different work for different companies, small, medium and large, whether it be due diligence, desktop studies, contract reviews, a whole range of different things. So today I'm going to cover a couple of things. Firstly, the many career pathways that are yours for the taking as a chemical engineer. My own personal journey from a chemical engineer to a metallurgist. Also just a couple of lessons around it's never too late to make changes, whether it's with your study or with your career. The importance of professional associations. And then I'll cover off very briefly just a couple of words on professional ethics, ESG considerations, in particular social performance, and also the importance of ongoing professional development all throughout your careers. So to begin with, you've made a great decision if you're studying chemical engineering. It's a really versatile degree that allows for many different career pathways. You've got all the fundamentals there in terms of fluid flow, heat transfer and thermodynamics, and that can take you into oil and gas, pharmaceuticals, food, minerals and other resources. So I will specifically talk about moving into mineral processing or metallurgy, but you have so many options open to you. I actually started my journey as a chemical engineering student, so I'll take you through briefly how that all came to be. So I grew up in a small country town in Queensland, that had no mining whatsoever, very rural, pastoral type of community on the Darling Downs. I was the first person in my family to finish school, let alone go to university, so it was all uncharted territory. I loved mathematics and science, so engineering seemed to be the logical thing. And chemical engineering was originally what sparked my interest. So off I went to Queensland University, and the first year there is common, so do a little bit of everything. And then in second year I enrolled in ChemEng and was quite happy with that, but was then persuaded by the head of the Mining and Metallurgy Department to firstly apply for a scholarship with Mount Isa Mines at the time, which I did, and really that was life-changing for me. So not only from a financial point of view, which it absolutely was, I had to leave home to move to Brisbane to study. So just having that safety net of, being able to quit my terrible job that I had at KFC at the time, be able to buy a secondhand car was really, really important. And I would encourage all of you to apply for any kind of scholarships that do come across your radar. It's not just the financial support, the ability to be able to have mentoring, to have really meaningful vacation work is just so critical to making a difference and really standing out amongst the pack when it comes to being employed. So once I made the decision to change to what was then called mineral processing engineering, was really the best decision I ever made, not because I didn't like ChemEng. I still spent a lot of time in the ChemEng department, but really found that this was my passion, and I was so glad for that decision. So there's just a couple of pictures there in the top left-hand corner. The mining games, which sadly are not being run this year, but any of you who are also part of the IChemE will know all about the mining games and how much fun they are. They look quite different now than what they did back in 1990, but it was all a lot of fun. And just a couple of other pictures there at the Kalgoorlie nickel smelter with Western Mining, and at Mount Isa with the open pit there in the background. And I will point out that the young lady beside me in the middle photo and the other ladies in the Kalgoorlie photo were all chemical engineers who made their way into the minerals industry. So some perfect examples there. So back in those days, the idea of inclusion and diversity was kind of a foreign concept. That was my graduating class there in the mining and metallurgy department. So there was definitely, was very difficult to not turn up for a lecture because it would be noticed. But they were a great group of guys, mostly mining engineers in that picture, because we ended up only with 3 mineral processors in my particular year. And the fellow on the second from the right in the back row, Peter Hayes, was our pyromet lecturer, and it still lectures at Queensland Uni today. So terrific guy, hasn't changed a bit. So after graduation, I'll come back to that. So firstly, professional associations. So I gather that you're all part of IChemE, which is why you're here today, and belonging to an association, whichever one or whichever ones you choose, is incredibly valuable. So it gives you access to professionals, access to mentors, and a real strong ability to be able to connect to industry and really have experiences that will really stand you in good stead for the future and going for various job interviews. They also provide the opportunity for professional development, which is incredibly important, and really puts you on a pathway then to becoming chartered in whatever discipline that you choose. So belonging to those organisations, incredibly important, as well as, in many cases, the opportunity to apply for scholarships. So post-graduation, my next piece of advice is take every opportunity that comes your way, because the opportunities really are limitless. After graduation, I went back up to Mount Isa for a number of years, got a really good grounding there in a lot of different mineral processing aspects. I then set out into the mineral sands sector, which was quite different again, and looking at electrostatic and electrostatic magnetic gravity separation, some kiln work with synthetic rutile as well. So different processes there. Also had the opportunity to be involved in tailings management and co-disposal of sand tailings with slimes, which was something that later became incredibly important part of my career. And I have been called upon to be an expert witness in a tailings-related matter on and off for the last 10 years. So very topical area and highly relevant for the type of skills as chemical engineers that you will have. So after spending my time in mineral sands, which was all across Australia, and with Iluka, then on a startup project in Murray Basin, I left then mineral sands after 10 years there, and took up a position in Adelaide with Amdel, now Bureau Veritas. So that was then a foray into management role. Ultimately, I was the general manager there of minerals and industrials. So that included the mineral processing, geoanalytical, petroleum, materials testing. So a wide variety of processes there across a number of states. So at that time was when the Olympic Dam expansion project was really underway with the geometallurgy program, which I had under my portfolio. And we had, at that time, I had about 750 staff working 24/7. So a very different type of role, but really enjoyable nonetheless, and an opportunity to work with a lot of really big companies, but also a lot of junior companies, which was a great experience. So after leaving Amdel, that's when I set up my consultancy, and have had that now for past 11 years, and really enjoyed that opportunity to get back into the technical game, and also to be exposed to a lot of different styles of mineralization. So in addition to mineral sands, I've consulted in base metals, uranium, and graphite and lithium, which have become more in vogue in the last 5 or 6 years. So really great opportunity to do so many different things. Couple of pictures there of some of the opportunities I've had. You can see Megan Clark there, who heads up the space agency. She delivered a distinguished lecture for us. The next photo down on the left with George Brandis in London at a summit that we held there. So fantastic opportunity to move around. A couple more photos there. The top left one was in India earlier this year, just before lockdown, with the Mining Engineering Association of India there. And on the top right was PDAC in Toronto 2 years ago with Austrade and Geoscience Australia. And then on the bottom, we've got Arequipa in Peru with the Global Minerals Professional Alliance, which is a wonderful body of all the professional mining associations across the globe. And then in the final one there, signing an MOU this year with the Indian Institute of Technology, Indian School of Mines, which is the largest mining engineering university in the world. So fantastic, lot of opportunities there. So I'll just touch briefly on professional ethics now and ESG. In terms of ESG, for those who aren't familiar with the term, it's environmental, social and governance. Of particular interest in the last 5 or so years for me personally and for the mineral sector has been social performance, and sometimes termed as social license to operate. And really it is not a nice to have, it is and it's not a cost of doing business. It really is it is essential for operation of a modern mining operation. So, and it makes good business sense. So we have all seen what can go wrong in this area when it comes to social performance, and whether that's environmental issues or cultural heritage matters. There are all kinds of things that then can really make or break a project. So it's an incredibly important part of what we all do. And professional ethics, I'm sure that part of IChemE's charter is to sign off on a code of ethics, which is enforceable for members. And that's also a very important part of being part of a professional body and being accredited. So I've already talked a little about grabbing opportunities for professional development. So I might just talk a little bit more about the social performance. And this is something that the IChemE is literally rolling out right now. And that's a social responsibility framework, which we're very excited about. And there's a couple of aspects of that. And one part of that will be a social responsibility public statement that members will sign up to. Our Royal Charter actually has at its core for our purpose is delivering value to community. However, community is not very well defined in the Royal Charter, which, you know, 60 years old. IChemE's been around for 127 years, so there is a need to modernise some aspects there. So we are now incorporating this social responsibility statement and also a chartered professional discipline category for social performance, and that's we're the first organisation to actually acknowledge social performance as a profession in its own right, and really excited about the response that we've had to that globally. And I should also point out that the IChemE is a global body, so 25% of our members are outside of Australasia, and that's another really important part of being a professional and having professional mobility, certainly back when we're able to travel again. So I think my time is up now, so I will say thank you, and really looking forward to the Q&A that's about to start. So I'll hand back to Thomas now.
The founder and managing director of Metallurgical Systems, which specializes in process design, simulation, and digital technology for the metallurgy industry. John will be joining us to answer the question, what's the worst that could happen? Thank you, John.
Same. Yeah. I was actually starting to think I also should have dug up some photos, although you would have had to scan mine in as well. So, so why do I have UNSW here? So I guess this is where my story starts. Like I completed a Bachelor of Engineering in Industrial Chemistry at the UNSW. And it's funny because when I look back as to why that I did industrial chemistry, it all comes back to I liked chemistry and technology, and my oldest sister thought I would enjoy it. And she was an electrical engineer. So I thought I'd just give it a go. I had no idea what to choose, so I just chose what could fit right. So from there I could figure what's the worst that could happen. So now they say ChemEng industrial chemistry is either the worst 4 years of your life or the best 7. It really depends on how you want to play your cards. It's funny though, because training engineers that can go out into the workplace is not so much about teaching about particular engineering topics, but about giving young engineers the vocabulary they need to be an active participant when they go out into the workforce and not hold everyone down. So when you get out of this, when you get out of university and go out into the industry, this is where the the learning really ramps up. And as Janine pointed out, this is where professional development is actually really important. Now, once I graduated, well, actually, I'll first go into my internship. So at the end of third year, I actually was an intern at an oil refinery. Now, this was a great experience and actually a real privilege to work there. Better yet, it was actually one of the better paid internships you could get. So as I was supporting myself, that was an extra bonus. A couple of highlights of my internship. So this was over a 3-month period. I got to see the inside of some vessels during shutdowns, which is actually really interesting to see in practice. I was actually in the safety office once where they had a loss of diesel containment from a vessel which occurred, and quickly saw how everyone responded. The first thing they checked was what was the lower explosive limit and what was the ignition temperatures. And that was all at their fingertips. What I also learned that it's sometimes better to use a steam lance to stop a fire. And that's an important lesson to learn, let me tell you. I also learned how to drive a fire truck on site and test mobile water monitors. I climbed to the top of every stack that I was allowed to climb. I used the site noise dosimetry equipment to validate the performance of the car stereo that I installed, 138 dB. I was then promptly given a noise dosimetry project by my supervisor, so I understood the damage I could do to my hearing and the risk involved with noise exposure. One thing that I really noticed is the industry was really old at that stage within oil refinery, and it did seem that there was not much investment or room for improvement. It seemed like the status quo was the target. I could see the place didn't have much of a future. And even 20 years ago, it seemed that there was no future in oil refining in Australia because what was happening was starting to be shipped from other countries. So even all that time ago, it didn't sound like a great idea. If people only stood the role energy sources play in our lives, the problem is energy is so underrated by the general population. Most of us just don't realise the role it plays in our lives. Now, energy is an enormous issue and is only escalating. Just remember, Australia keeps 14 days strategic reserve of fuel oil products. Current consumption estimates prior to COVID-19 place it at closer to 10 days. I suspect many of you could make a wonderful career in this area. Now, at the end of fourth year, I was actually offered 2 roles. One was back at the oil refinery, and the other one was as a consultant for about half the amount that the oil refinery was offering me. So I did what any good engineer would do. I chose the low-paying role. It's only money, right? When I let the refinery know, I was told by the hiring engineer that I was making the right decision. That refinery is now closed now, along with most of the others in Australia, but I may digress if I don't keep going. So I chose the consulting role. Now, this was a fun role. The first day I was shown to my desk, the PC was so old, in fact, older than my home computer, that it took 15 minutes to start up in the morning. Now, I'm not exaggerating. It was a 75 megahertz single core PC, which means roughly an iPhone 11 is 200 times more powerful, just on a clock cycle basis. And that's before you include all the parallel processing. Now, the lack of tech is a bit of a tale of contrast because data processing was slow, but not everyone had a camera on their phone. So there is a lot to be said for growing up at a time when there was nowhere to post photos and videos. But once again, I digress. Now, despite the lack of technology, I still approached this role with a lot of enthusiasm. It was actually a lot of fun. I was in a team of 3 process engineers working on the ANSTO Opal reactor, plus a whole bunch of other projects ranging from designing weirs and massive dust suppression systems to designing manifolds and bearings. It really was quite diverse. One of the highlights for me in that role was I was on site at the Opal reactor after they'd recently poured the high density concrete that formed the core of the reactor. And as I walked past, I figured this was probably my only opportunity to stand at the bottom of the reactor pool. Now that's something you just can't do anymore. As part of this role, I was also part of the graduate program and I had a mentor assigned to me. Now, this was actually a really beneficial program because the mentor was a partner of the firm and a very successful electrical engineer. He mostly worked on mobile phone network tower rollouts, so a lot of project management type work. I've had probably 4 or 5 30-minute chats with him over my 2 years there. The funny thing is, one thing he's actually said to me has always stuck through. If you can be a specialist before you're 30, then specialists are always in demand. And the good thing is, a specialist before you're 30 is an expert before you're 40 and a guru before you're 50. There are no shortcuts. Now, this role went on for a while, but eventually both the senior process engineers left that company just as I was finishing my graduate program. This is what we refer to in the industry as a battlefield promotion. Suddenly the graduate's in charge. So as part of the closeout to the graduate program, the company CEO gave us a pep talk. So this experience always sticks with me from this role, because to the group of graduates, he spoke about how the company was structured, the role of each engineer has, and how the company retains staff by allowing a shares buy-in program. Interestingly, he didn't actually mention chemical engineers. So when the time came, I asked, what role do chemical engineers play here? He replied, they don't have a role. No chemical engineers work here. So that was about all the warning I needed. So what I did is I did what any sensible engineer would do. I actually joined the Air Force. So from there, I actually joined the Air Force as a pilot. Now, this was an incredible experience, especially when you think about the opportunity to fly some of these very high performance aircraft. So during my time there, I actually got to fly the CT-4, the PC-9, and the BAE Hawk, so the Hawk 127. Now, this was really valuable in the fact that I took a few things away from this experience. The first one is, and this is a really important one, stress is relative. It's important to remember that if you're not within a few seconds of hitting the ground, you're not on fire, or nobody's shooting at you, then things could always be worse. The other thing is, when an opportunity presents that interests you, you should absolutely take it, because you never know where it may lead, and you may never know if you'll see that opportunity again. And the last one is, there's a lot you can learn. There's a lot you cannot learn from a book. So it's important sometimes to actually get outside and try and do. So after this experience, when I discharged, I found myself out in Perth. So my wife and I were really enjoying living in Perth. So we figured we should just see if we could find some engineering work. This was before the resource boom in the industry, and it was just as it was picking up pace. So whether it was good luck or good management, I mean, I'll take either. I found myself in the right location at the right time. I applied to a lot of companies, and that's an important part of this story for later. But I ended up at a small engineering services company specializing in process simulation. I was their first full-time engineer outside the founders and a couple of the part-time engineers. And this is where I found my area of specialization. I really enjoyed process design and simulation, particularly in hydrometallurgy. And in fact, after university, after our design projects, this is an industry I tried to get into and couldn't find any opportunity in. So when I was here, I worked on so many projects over that first 2 years as the industry really ramped up. I can't even start to list them all. They were all over the globe, and predominantly in nickel, cobalt, copper, uranium, and a little bit of platinum group metals. And after a few years, I actually even found myself as one of the leading engineers in our field based in Perth. So you can learn a lot, or you can learn very rapidly when you're in a small, highly capable team. And that's something that I think I've always enjoyed. Being part of a really small team of talented individuals is really the fastest way to learn and just improve your skills. Now, this was a really interesting role because as I was a reasonably junior engineer, you don't have a lot of street cred, but what was great is I often got the opportunity to go to the client meetings. Now, this was with usually, industry heavyweights and everyone, where they would discuss all the technical aspects of the project. And as the junior engineer, I was expected to take minutes. Now, the engineers would discuss, argue about all sorts of things, and just being in the room was incredibly valuable. Now, also being there and being held accountable for recording all the points and decisions was a great way to learn from all these engineers. You had to keep up, so you had to be quick. So during the first 6 months of this role, I was contacted also by a lot of other resource companies who encouraged me to come for interviews and consider roles with them. This is really where, as the boom was starting in Perth back in the mid-2000s. Now, all the roles sounded great, but the overriding feeling I had at the time was I was happy where I was. So if it's not broken, don't change it. So I stuck in this role for a couple of years. And the company grew to be about 16 engineers, and I found myself as one of the leading engineers there. Now, what's interesting is, as things get bigger in any company, I found that there was a lot more expected of me in my role, but the opportunity to maintain my rate of learning started to be hampered. And that was when you have, I guess, the ingress of non-technical managers that, sit above you in the hierarchy. So as I was a technical specialist, I wanted to stay in that field. So it seemed that during my time at CEUS, I managed to impress a few people in the industry. Now, although I was really happy in my role, the fact that I had a limited ability to learn, it really gave me a push to consider other options. That is when I found out that there were 3 separate companies that wanted to hire me. So at this stage, what happened is my wife encouraged me to set up my own consulting business and to try and work for all of them. So nothing was stopping me, so what's the worst that could happen? I figure if it doesn't work out, I can always get a real job. So we came up with a name and set some goals. So my first company, Elemental Engineering, was founded. Now, this company specialized in process design and simulation, and particularly nickel, cobalt, copper, uranium, and platinum group metals. I developed a reputation for being a person that can figure out the difficult stuff. So that's really how it all started. Now, funnily enough, from day one, I was busy. And in fact, if we go back to the previous story where I applied to lots of companies, one of the companies, when I left the Air Force, rejected my resume applications and actually stated they weren't looking for pilots, they were looking for engineers. Now, funnily enough, they were my first customer, and they basically underpinned the whole initial success of the company, which is always important to remember, that the industry is small and there's lots of opportunities, and never take things personally. So that's how it started. So from there, in my first 2 years, I was probably working 80 to 100 hours a week. I was turning away work so often that a friend of mine actually said that he had another friend that also did the same sort of work. So it was looking for a job. So we met and we hired him, and that's where it went from there. Now, I haven't actually mentioned the role others played in the success of Elemental. Now, this is a key thing to remember in our industry. Metallurgy is a really small industry. Now, I had the opportunity to work with some of the real industry-leading experts, and there were 4 in particular. And without their support, I simply could not have achieved all I wanted to do. Like, I learned more from working with them than I could actually imagine. And don't get me wrong, they were very difficult taskmasters, but that was always fair. We worked as a close team, often sat in a room together discussing interpreting data and implementing within simulations. Often the industry guys would advocate for us to be part of their project because we had the complementary skill sets. So in those first few years, the main things I can take from that is, when given an opportunity, take it. Sometimes I was given tasks that I thought were impossible to achieve. I stated that up front, but then I dried my eyes and got to it. And I always managed to get the work done. So clearly it was possible. I missed out on some weekends and even had to interrupt holidays, but it's important not to let people down when they give you an opportunity. Also, there are no guarantees that you'll be given a second chance or opportunity if you turn people down. So don't let them down. And remember, the reward for good work is more work. So then we expand. So a couple of years in, or a few years in to my elemental engineering, I was finding that I was lying in bed for 8 hours every night doing nothing. So I figured I should try something else. I realized a lot of the data system plants were incredibly poor. So the data was stored in all sorts of locations, and in many cases, people would make it very difficult to access. The reason people do this is to limit transparency. If no one can access the data, then you can't hold them accountable. This is actually quite a big problem in our industry, and to be honest, I suspect all industries. So I decided, rather than to complain about it, I should try and come up with a solution. Once again, what's the worst that could happen? So effectively, all the money I earned in Elemental went in to support the development of metallurgical systems. And funnily enough, one of our clients from Elemental Engineering was our foundation client in metallurgical systems, because he knew that we wouldn't let him down. Now, when you're starting a technology company, the key is you need a foundation client, because you need to test your software in a, let's call it a live fire scenario. Now, 10 years on, Metallurgical Systems, which is my software company, has a product called Metallurgical Intelligence, which has a number of different components. These components are deployed across 22 sites in 3 languages in 9 countries, I think, at last count. So you never really know where these things can lead you to. Now, I guess as a metallurgist, what is your role? And this is what a lot of people don't understand. So your role as an engineer is to develop technical solutions, economical solutions to technical problems. That's effectively the definition. Now, the key is, how do you go about doing that? Now, often you need to understand the information. So you need to have an idea. You need to be able to investigate that idea. And then if it's worthy, be able to present and communicate it to other people. This is a core skill that every engineer needs, the ability to present a data-driven argument and to show it to someone and to get them to understand what data you used, how you did it, and why this is a good idea, but also be open to the fact that you may have misinterpreted data. Now, once you go through the communication, you now can get buy-in, you have to implement it and measure the result. Now, this is something our industry doesn't really do. Often when we implement nice projects, we don't often go back to measure to make sure that we actually have done it correctly. So this is something as an engineer you constantly want to do. You want to be able to communicate, implement, measure the result, and start again. The faster you can do that, the more value you add and the more you do. Now, one key thing you need to also do is somehow link that to the performance of the plant. So what you need to do is be able to find out how to communicate all your findings and results and link it to things that are reported to the wider organization. So therefore you can actually see. And in metallurgy, this is actually linked to all the metallurgical accounting. Now, one thing I find in some plants is they don't always have great data systems. So what needs to happen is, if they're not there, you need to advocate for them, because this is what empowers you to be able to do what you need to do as an engineer. I mean, as an engineer, you're effectively useless without data. You can't develop, you can't continue. So it's really important that once you're out there, that you can actually advocate for these systems to be put in place. Now, if I link back to why metallurgy is actually incredibly interesting and fun. It's very variable. So often people think the building blocks are the same, but there's always little subtleties in geology that you need to solve. So it's a constant problem solving and optimization type of work. So it's actually very interesting and evolves quite well. And it's global. So for example, from Elemental, I've worked all over the world. And in particular, Metallurgical Systems does 100% all international work. So the opportunities to travel through Africa, South America, US, Kazakhstan, Europe are endless, and they're wonderful opportunities. So metallurgy really does take you places. So what do you really need to succeed in this? I would say enthusiasm's the key, your data analysis skills, and your communication, and always keeping an open mind when it comes to data. So they're the key things you want to bring with you as a metallurgist or a chemical engineer. Now, a last sort of thing to remember, that once you leave uni and you go out into the industry, what you'll find, it's a very small world. So the people that you meet along the way often have a habit of popping up again. So for example, the professor that taught me process design at university is now a client, one of our process design clients. So things tend to circle. And for example, my girlfriend at university is now my wife, and we have 2 sons, 2 businesses, and a 23-year history. So it's amazing the people that you meet along the way, and plus all your friends. So if you're still at uni, enjoy it, no matter how it's sort of presenting and the challenges that are there. And if you get into the industry, the most important thing you can do is tackle things with the enthusiasm and sometimes just go, what's the worst that could happen? And that's it for me.
Thank you, John. That was really great. I learned a lot. I'm sure that everyone else will be able to take something away from that as well. Last before the panel, we have Dr. Leon Prentice, the Research Director for the Metal Industries at the CSIRO. Within the Metal Industries program, strategic fundamental research is conducted with commercial outcomes across key areas such as aerospace, Australian defence, rail and mining, energy, and medical device metals. Leon will be joining us to talk about opportunities for additive manufacturing and why production engineers should care about research. Thank you, Leon.
found that really entertaining. Thanks, John. That was very... I think one of the things that I'm hoping that all of the people listening to this get out of this is a real connection and synergy between the things that we're presenting and things that we're doing. I'm going to be talking kind of further downstream in the metallurgical space around metals, what we do with them. I'll be talking about some of the big picture around this at the very, very big picture, and then at one very specific example of how you might use metallic additive manufacturing in process industries. But let me start off with talking about what drives me in particular. So my journey, I'm just summing up here on one slide. I did grow up somewhere that was poor. You can win a prize if you can work out the shape of that country and its flag. Drum roll. Yes, that was Tanzania. I then studied at Melbourne Uni, and I really liked John's point just then about the 7 best years of your life. That undergrad was the 7 best years of my life. I had great fun doing not only chemical engineering, but science and a little bit of history as well. You may be aware that it is Bastille Day. I got to do some French Revolution and American Revolution. I then spent a bit of time working with BHP and with CECL in North America before coming back to Australia, working in materials engineering downstream. So SDI is a dental materials company. So I used my chemical engineering knowledge in ways of manufacturing high-tech products, high-tech materials. Melbourne Uni was kind enough to let me enroll and let me, I guess, collate some of the things I published, and gave me a PhD out of that, which was very kind of them. But I guess to take on John's point about specialization, I realized at the end of some time at SDI that the dental materials field is actually very small, and I was one of probably about 40 people in the world who did what I did, and I wanted to do something more broad, something bigger. And so CSIRO is the answer to that. At CSIRO, you get to do many, many different things, as I'll introduce very shortly. And CSIRO has also let me do extra training and development as we go along. I've put under there some of those professional bodies. So kudos to Janine. That's exactly right. Let me I guess, add my support to the statement of getting involved in professional bodies is really important, really useful. I've had the pleasure of being involved in each of those organisations down there a fair bit. Sorry, Janine, I haven't got stuck into IChemE as much as you or I would probably like. But I've certainly been involved in a number of these, and at the moment, in particular, I serve on IChemE's Learned Society Committee. I'll tell you a little bit more about that later on. So what sort of things drive me? This is some of my family, some of the things we like to do. You can see we like being outside. You can see we like studying. That was my wife's PhD graduation last year. She's a neonatologist and a bioethicist and does some really cool work just near here at the Royal Children's Hospital in Melbourne. So I do spend a lot of time home with the kids. That's one of the things I do, as well as working. Another thing that inspires me, I did need to put an aircraft up. I'm not sure if you've actually flown this one, John. If you have, I'm very, very jealous because all I've done is got close to it. The SR-71 Blackbird is just a marvel of engineering materials. The processing that's gone into this, the titanium content of it, the fluid dynamics of the engines and the sonic shocks that you see there. I just love technology like this. So if I did get to ride in one, actually they're all grounded at the moment, but that would be a dream. Another thing that drives me is Australia's critical mineral strategy. So in Australia, we have a lot of resources in the ground. We do not much with them, to be honest. We do dig up a lot of iron ore, we do dig up a lot of coal, and we ship them overseas. But we have a whole lot of high value metals that we do very, very little with. So one of the takeaways I want you to take from this maybe is that these opportunities are huge. This list, critical mineral strategy, to my view, is actually not so much a mineral strategy, it's actually a metals strategy, because aside from maybe graphite and helium, the focus here is on the metals that's part of this, and illustrating that Australia's production of most of these is very, very low. Another thing that drives me is shifting the diversity metrics in the profession. When I took over as Program Director of Metal Industries, that was our leadership team. We did get a professional photo done, but I've never used that as a professional photo because we're a bunch of white blokes, really, and that's just unacceptable for us to share. But I have shifted the metrics on that, and really excited that we have a new active materials science leader. That's Antonella. She's down there in the bottom right. She started earlier this year, before lockdown, and she's just recruiting her first postdoctoral fellow. So those are some of the things that drive me. Let me give you just a little bit about CSIRO as a whole, because I think it's worth introducing a little bit about what we do. We are Australia's national science agency. We have roughly 5,500 people, mostly in Australia, though there are also offices in Australia, Singapore, Vietnam, US, and Chile. There's a US presence is reasonably substantial, being an office in Silicon Valley, representatives in Houston and Washington, and an embedded person with Boeing in Seattle. We do have 57 sites, so you'll find us all over the place. I work in Clayton in Victoria. That's the largest site, particularly when it comes to manufacturing and minerals. We do a whole lot of work with the innovation space, so the patents and licenses, spinning out companies, working with partners across the whole value chain. So we do work with just about most people in this space, and our main goal is to grow companies, to see things grow and develop. You'll see also there's school students. The high school students is part of what we do, but we even more do co-supervising masters, PhDs, and postdoctoral ongoing professional development. We do work on these big picture challenges. We like to think that we work on what are the really big picture tough things. I'm part of Future Industries, but we work in everything from Antarctic exploration to space. So some of the topics are there that we work in. You will have seen CSIRO in a lot of the media. A lot of different areas are out there. Mining and manufacturing is a key part of that, as is renewables and energy. So my particular research program, very briefly, is part of manufacturing. We do also have a minerals business unit that's just next door to us, and we work closely with their processing research program. The way I put it when I'm talking to people who are chemically inclined, which is all of this crowd, is that we're looking to reduce the average valency of Australia's exports. So you guys are chemical engineers. You can think of this in terms of, what does this actually mean? It means we want Australia to be making more metal parts, not the ores. We want to be shipping less material. We want to actually be reducing it and then making useful things out of it. We work in the battery space a fair bit. We want to be shipping charged batteries and less of the e-waste that we send overseas. We want to work on reducing corrosion and increasing the sustainment of all our facilities and equipment, from mine sites to submarines. So that's how I put it when I talk out there. This slide has a bit more information if you really want me to get into detail, but I'm not planning to do that. You can just see up there in the top right some of the areas, particular domains that we as Metal Industries focus in. Aerospace, defence manufacturing, transport and resources, that's some of the mining and rail. Energy metals, that's the battery space, and then medical metals, and I'll touch on that very shortly. The metal value chains is also on there because in some particular strategic metals, namely titanium, lithium, scandium, vanadium, a couple of others, we want to work to grow Australia's value chain as a whole, from the mine site to the finished product. I'm going to be talking a bit about additive manufacturing. And so to introduce what we do in metallic additive manufacturing, we call this Lab 22. The 22 is for titanium, if you keep track of which element is which. Because it's our favorite, because we've worked for a very long time in titanium, we love it. In fact, I wear titanium, including a cold sprayed titanium ring. So we have a lot of equipment in this space. Typically, these machines would set people back somewhere between $2/3 and $1.5 million. But we have invested in them primarily to help kickstart the industry in this space. So we do, I think, still have the largest facility in the Southern Hemisphere, mostly located in Clayton, though we do have a machine in Sydney as well. And we've worked in this space to grow this industry for quite some time. Just to touch on additive manufacturing, for those who haven't come across it before, there are many different ways of doing it. So fundamentally, you can think of it as joining at microscopic scale, bit by bit, welding, so to speak. And you can think of it in terms of how you introduce your material and how you introduce your energy for deposition. There are many different ways this can take place. The typical ways, or the most common ways, are blowing a powder into a laser beam, and so you melt it and you build up your structure that way. You can also do as a powder bed. So the powder bed system with either a laser or an electron beam is probably the most common around the world now. It's roughly 80% of the market. And then there's a wire feed, an electron beam, or again a laser that's often used for larger parts. So this super duper video that you're not going to get to see shows you what it looks like to build up a part layer by layer. You lay down a layer of powder, you apply a laser beam in selected areas, you lay down the next layer of powder, and so on. This one that you'll also not see shows some of the computational modeling of that. This is a model done with, this was some time ago, so we only modeled 400,000 discrete particles, but this shows how they rake across a surface and what that does for the performance of the system. This is another beautiful video that shows a laser beam melting a powder bed as it goes across. If you want to know anything more about that, find me online somewhere. So one of the beauties of additive manufacturing is you can make all sorts of things you could not otherwise make by conventional means. This is one not from the minerals processing area, but this is sternum that we made for a patient who had a degenerative bone disorder, and so they needed to remove most of the patient's sternum. In this case, we 3D printed a titanium rib cage and sternum to replace what they had lost. You can see the bits there that particularly bolt into the rib cage. It's designed exactly for that patient with using their CT data, and there's actually flexibility in those. You can see from the thickness of the titanium spars that mirrors the flexibility that you have in your rib cage yourself. So that's an example of where it's gone to. If you do want to see more about Lab 22, there is a relatively recent CSIRO Lab 22 on YouTube, and you'll find us. Let me talk briefly about the very bigger picture. So when I'm talking to people thinking about their pathway or where they should focus their efforts, I think it's worth sometimes to take a little step back and look at the very, very big picture. CSIRO has worked on this. There's an Australia 2030 report. There's also another one looking at 2050 that looks at the impact of the future megatrends on these particular areas. And as you can see, these are areas that employ a lot of people and also employ a lot of chemical engineers. And one of the points here I wanted to make is that the annual R&D spend for most of these is pretty poor, to be honest. So mining and the met sector there is down at 1.7 out of $94 billion of industry value added. My perspective, the mining industry is not spending a lot of money on research, and it should for the reasons I gave earlier. But I guess my point is that what happens with these industries in the next 10, 20, 50 years will be highly dependent on what we develop and how we adapt as we go forward. So the global megatrends. I spent an hour presenting on this to a Women in Manufacturing event earlier this year. I'm not going to give you the hour summary. I'm just going to highlight these and put them up. So more from less is about the trend to do more, to do things more efficiently. You can see that in the continued push for efficiency in vehicles and transport. You can see it in farming. You can see it all over the place. Planetary pushback is really interesting. That's related to not only climate change, that is really, really important, but even at the smaller scale. So, for example, there was a great article just this week published about the interaction between ecology and the transmission of coronaviruses, and highlighting the fact that it was COVID-19 was kind of predictable. That was going to happen at some point. The Silk Highway highlights the rise of middle classes, particularly in South and East Asia, and the reconnection of those trading routes across there. Forever young, people are living longer lives and have higher expectations as they do. Digital immersion, people are far, far more connected, and that will just increase as the time goes on. Porous boundaries, admittedly that one is slightly shut down given that there's minimal international travel at the moment, but people in general are moving in between regions and professions much more than they used to. And then Great Expectations is about the rise of the middle class globally and how people are expecting more from their lives and more from their services they get. So one of the things I like to do is almost stop here, because I think it's worth you spending some time thinking about how your career pathway may be impacted by these trends, what sort of opportunities there are, and what sort of challenges there will be as these things progress over the next 10, 20, 50 years. To bring it down a level, the IChemE Learner Society Committee was formed last year. I'm one of the representatives on that. I'm responsible for resources and manufacturing as far as the sector area. And so I connect with IChemE's special interest groups around the world. When we met last year face-to-face in the UK, one of the things we tried to do was narrow down what should be the priority areas for IChemE. And we came up with these three: sustainable production, major hazards, identification and management, and digitalization. Now, I think that you'll see that these come into almost all of the things that I think are important and worth doing. You've seen how digitalization has come in, particularly with John's presentation just before. It's core. How does information get captured and move around in a plant or in a design or in a part that's actually out there in service? The major hazards piece, I think, is becoming increasingly critical. It's part of the hydrogen economy, right? What happens when and if we move towards hydrogen being a major fuel source, and someone wants to drive the Spirit of Tasmania from Melbourne to Tasmania with 3,000 tons of hydrogen on board? And most importantly, I guess, from my perspective, the sustainable production bit. In the metallurgical space, steel is roughly 8% of the planet's CO2 emissions. That's woeful. That is something that we should be working on very, very hard indeed. So let me give you one example. I'll spend a little bit of time on this because I'm hoping this gets your thoughts started around not only the research side, but on what's possible with new technologies. What can we do to shift the metric, the scheme of what we do? You'll see in the top right there some of the structures that we make in our Lab 22. The middle one there is actually a part that we made. We get asked occasionally for widgets or knickknacks for various diplomatic things. That one was for the celebration of the CSIRO, Chinese Academy of Sciences, 40th anniversary, which was a couple of years ago. And Prime Minister at the time, Malcolm Turnbull, presented that to Li Keqiang, the Chinese Prime Minister at the time. So how do catalytic static mixers work? And what's this got to do with process engineering? So that the metallurgy bit here is in the print and the coat. The chemical engineering bit is also not only in those parts, but in the react bit. Let me give credit here to some of my colleagues in the advanced fibers and chemical industry space in CSIRO. This is a collaborative project between them and us. So Christian and Yutong, whose picture that is, work in that advanced fibers and chemical industries. Dayalam and Darren work in my metal industries program. So fundamentally, we're making an interesting shape to put in a pipe and coating that with a catalyst. One can coat that through electroplating or cold spray or wash coating. You can see some of the sort of structures you get on the right in terms of the final part, what it looks like when it goes into your reactor. And then it goes into, first cab off the rank is a hydrogenation reaction. So in this case, you're using your static mixer to go inside the pipe, and then as you flow your material through, you get your reaction happening far more intensely and in a controlled way than you would in, for example, a large stirred tank reactor. So this has been done at multiple scales. There's a whole lab. If you would like to come and see this when we're out of lockdown, that can probably be arranged because we're pretty open with our research. So this has been done initially at very, very small scale and then building up to 12 catalytic static mixers, and then you can run 10 or 20 in a go. So with this type of system, you can get your process intensification very, very high. You can control very accurately your pressure. You can control your temperature as your materials go through. You can improve your yield very, very significantly. So this is for making active pharmaceutical ingredients. In this case is a hydrogenation reaction to make linozolid or Zyvox, which you may have heard of. It's a reasonably common antifungal. So with this type of system, there's no workup involved. There's no catalyst leaching. The amount of catalyst that ends up in the final thing is down at parts per billion level. And what you've done is develop a whole new process for making parts. The catalytic static mixer itself is the key here. So you get the continuous flow with a tubular reactor system, but you get the good process control and scalability from that. The static mixers are made using additive manufacturing. In our case, they're made using an electron beam powder bed system, normally out of titanium 6-4. The deposition methods are commercial, the catalyst systems, and you can see some of there what the structure looks like. Just to give you an idea, I thought I'd put up more science behind this. There is very fundamental research in some of the computational fluid dynamics, practical engineering, and the reaction kinetics that goes into this. This is a paper that was published last year. You can see some of the images down in the bottom left of what the actual surface looks like. You can see it's not a pure smooth surface. Those particles that you can see on the right of that picture in the bottom left are some of the residual unmelted particles from the electron beam powder bed system. You can see some of the flow modeling with that, and you can even see I did need to include a Reynolds number in this somewhere. I can hear you all cheering silently as you watch this because somebody needed some equations about mass transport and a Reynolds number. So part of the pathway at CSIRO is around this commercialization and scale up. How we do more of that process R&D, how we partner with people to accelerate this, because as CSIRO, we're not going to be commercial ourselves. We want to see this technology taken up out there. In this case, it's being taken up partly by Precision Plating. They're a company who are looking at how they can sell specific catalytic static mixers for specific reactions to industry. So these things are also being taken up. Boron molecular is there on the right. You may have, for those who are particularly astute about investments, etc., boron molecular just announced a major deal with Korea and CSIRO, wherein CSIRO has some equity in boron molecular, and they'll be part of the vehicle for how this gets scaled up. So I wanted to stop there. I'm more than happy to go on and answer more questions after this. I'm really looking forward to what this panel brings out. I'm really keen to connect with all of you. So let me hand back to Jack, who's going to take us through and moderate the panel.
Thank you very much, Leon. So just first of all, I'd like to welcome all of the people attending. Please ask any questions, even if you think it's not a good question. I'm sure that someone else is likely thinking of it and they would like to hear the answers. So Janine is coming on, and John as well. So we'll start with a question from Miranda. So this is directed at John. You mentioned that you graduated with an industrial chemistry degree at UNSW. They're also doing this degree, and they found that industrial chem leans more to chemistry rather than process plant control and simulation, or at least in her experience. So how relevant is your degree to the process engineering job in oil refinery industry?
Okay, so I'm assuming you can hear. So I actually work in the metallurgy industry, and what you learn in industrial chemistry is incredibly relevant. It's in fact a bit of a funny story. So when I was actually doing industrial chemistry, it wasn't applied science. And then about 2 years in, I realized that the industry valued engineering degrees more. So I actually went to the head of school and said, okay, I'm going to switch to chemical engineering because I'm doing all this extra chemistry work, and then I'm getting out of the degree with effectively a Bachelor of Science as opposed to a Bachelor of Engineering. And what actually happened is that catalyzed a change in the way they recognise that degree, because the only difference was a phenomena transport subject and one other minor one. So I said, okay, well, I'll just do those two and switched to engineering. So as part of that, they turned around and made a Bachelor of Engineering of industrial chemistry. Now, yes, it leans towards more chemistry, but to be honest with you, that's more the fun part of metallurgy and chemical engineering. So it's much of a muchness, and all you're doing is learning the language, as I said. You'll actually really start learning everything once you get out into the industry. So don't think that that's holding you back at all.
Thank you very much. Okay, I got another question here also for John. You mentioned the importance of specializing early on in your career. So do you have any tips for building your skills in any specific area?
Not really. I guess I can only draw on my own experience. And that was just a piece of advice that an old crusty engineer gave me, and for some reason stuck. And the thing is, what you'll find in our industry is if you are a specialist, you're always in demand. Now, as for finding your own, I would say do whatever you find is interesting and fun. And there's plenty of options out there in metallurgy. So if you do find something and you're given even half a chance to work in that area, jump at it with both, with both feet. Cancel your holidays for the weekend. Do whatever you need to do to make that work, because once you've got your foot in the door, the rest will open up. So I would say just do whatever feels fit at the time. And look, you don't have to be a specialist before you're 30. I mean, you can. There are ways to fast track it by working more, but it's one of those things that if you can be earlier or recognize it earlier, then you have a greater chance of success.
Thanks, Leon. Janine, do you agree?
Can I just second that? I think that approach of finding what you love doing and then looking for someone to pay you while you do it is a great thing. I mean, I say this also in terms of research. If people really want to do a master's or a PhD in something, try and make the way, right? If you find a supervisor and you find someone who's willing to support you while you do it, then just go for it.
That's some great advice. I've got a question from Coco. So this is to everyone. To what extent has the safety culture changed in the metallurgy industry? And will it continue to change or start to if it hasn't changed?
I'll go last if you want, Janine, because
all right. Well, I'll jump in then. I think the safety culture has changed significantly already. certainly in the resources sector. And I would see now the new wave coming through is more on that social performance side. So I think the implementation, the integration of safety is really well established now over a couple of decades. So, which is a really positive thing, but not something to become complacent about. But if you think about some of the risks that are out there in terms of, high pressure, high temperatures, various chemicals, reagents, etc., manual lifting, a lot of this stuff is now done by robotics. And there's a lot. The standards are really incredibly advanced, I think, in the safety area.
Yeah, I think a lot of incredible things have been done in safety and will continue to. Integration of technology into more and more so that we're exposed to less risks. So I think that's an area that particularly Australian companies have done a lot in, but it's actually at a good standard and continually improving because everyone takes it very seriously.
Yeah, I'd just add a personal call. If people are worried about safety, do something about it. Right? If you're ever in a situation, particularly as an intern or a graduate engineer, and you don't know what you're doing, please don't do it. Right? If you're working for a company that somehow puts production above safety, then do something about it. Quit or blow a whistle. Just the standard you walk past is a standard you accept. So make it personal.
Thanks for those wise words, Leon. So I got a question from Thomas. How has the industry changed since you started your careers? Where do you think this shift might have come from?
I'll go for it. I mean, the biggest change that I've seen, and I'm a little bit biased on things, is the application of digital technologies. Like, that's something that I think the industry is just coming to terms with the invention of the computer. And now that that's in play, things like making data accessible, transparent, to everyone is really the core of what's happening a lot of the moment. A lot of the technical aspects around processing technology are constantly evolving, but at a much slower rate. So I would say the introduction of digital technologies and those applications are probably the fastest changing thing at the moment, certainly in my area.
Yeah, I would second that, John. And the rate of change, I think, is also something that has been quite exponential. So for someone of my era, we were lucky to have a calculator at university, let alone a computer. And the whole idea of turning on your computer when you got to work and going to make a cup of coffee and waiting another 15 minutes to turn it on, and the same to turn it off, is sadly doesn't seem that far away for people like us. So, but I think now the technology right now, if you think about what we would be doing under this current uncertain situation that we face ourselves with, if we did not have this technology to be able to connect with each other digitally, it would be a completely different scenario. So I'm forever thankful that the technology's evolved to where it is to keep us connected.
And the digital technology actually makes our jobs fun. Like, being able to access all that data and play around with it and analyze it is actually fun. So those technologies are really enabling the work to become more enjoyable and faster. So, and you can get more done quicker. Sorry, Leon.
I was going to agree. I guess I was probably going to offer a lament on the flip side that often change is very, very slow, particularly in major process industries. I mean, it really, developing a new process takes a long time. I mean, I worked with CECL in Vancouver back in, this will date me a bit, right, 99. And it took another decade before that actually got to commercial. And that was a demonstration plant. We were making a ton a day of copper, but it took another decade before it actually got fully commercial.
Yeah, and I think that's another aspect of the sector that can't be underestimated is in a number of sectors, you have the philosophy of fail fast, pivot, fail fast, pivot again. There are some elements of our industry that you simply can't do that. So if you're designing a SAG mill or a tailings storage facility, you cannot afford to fail. So often there is that kind of inherent prudence there when it comes to designing things.
Great stuff. Actually, that really brings to mind when I spoke to some people in design. They mentioned that, especially in Australia, in the metals and metallurgy departments, that people were very cautious with new processes that ask, has this been done before? Has it been done before in Australia? Those types of questions before you even consider it. And it's really a testament to, in the metallurgy field, how you just can't make changes without being sure that it won't affect people and livelihoods.
But being sure and being paralysed by your thought of risk are two different things. So, for example, those technologies get implemented all over the world at multiple locations. So sometimes, Australia's a little bit slow to adopt technology. You get to see the first 10 how they go, but you could have had that efficiency boost 20 years ago if you really wanted, or 10 years ago. So there is always a balance. Like, I think sometimes there's a tendency to be maybe too conservative with some things.
And it also depends on who's funding the project or who's championing it. If certain people are prepared to take greater risk for reward. So
that's technical risk, not safety risks. That's
true. True.
Of course, always. Thomas got a question for John. So, did you do anything differently when you started metallurgical systems as opposed to when you started elemental engineering?
To be honest, not really. Like, really, elemental was great and I was really, really busy. But what I guess saw the limitation in consulting was you kind of have to pay by the time you're sitting at your desk. So the business model isn't as strong. So really, that's how I got to metallurgical systems. I just thought it could be done better, and it was quite funny. I thought I could probably build a prototype in a few months and do this. That was ridiculous. There is so much work involved. Even like, it's quite funny now. We often to present to companies, they go, "Oh, that seems really simple. We could probably do that." It's like, it's taken us 400,000 hours of development time to get us to this point. It's so no, I don't think I did anything specifically differently. I guess the key to all the success of these organizations is actually finding the right people and making it worth their while to stick around. Particularly in software development, continuity in your developers and your core team is really, really important, because it means you can do things quicker. If you're constantly retraining people, it's difficult. And to be honest, it's the same with engineering. So in our simulation process design side, I find it normally takes between 1 year to 2 years to get people to sort of up to a standard where they're sort of self-sustaining. There's a lot to learn.
That's great to hear. I got a question from Bigalo. So I hope I pronounced that right. With the current COVID situation and impact on employability and other parts of our lives, what do you think as students would be some of the steps to proactively act within the industry or even outside the industry, if you've got any great tips? So an example, more investment in education and specializing through masters, or other types of things we could do.
I'll jump in firstly. So I think the wonderful, there's obviously been a lot of negatives with the current situation, but there's also been some positives. And I think the resources sector has come into its own here to be classified as an essential service. So I think that the example that's been set by the industry with FIFO and other operations continuing through, and importantly continuing through really safely with no incidents, is a great testament to the maturity of the sector. So I guess my tip is definitely to increase your credentials. And if you are interested in doing extra study, by all means do that. But also don't be afraid to get out into the sector, because we still need hands-on people to come in and start working on sites.
Yeah, and I would also add that there are still a lot of companies employing, and that it's still busy. So there is actually opportunity. So keep out there. And this is, once again, if we loop back to things like professional development, being involved in IChemE, for example, events, will actually get to meet people within the industry. It's amazing the effect that can have if you leave someone with a good impression. And if they're suddenly hiring, and like I said, it's a small industry, and I still remember people that I'd met a few years ago when I thought they're good, and go back to them. So if they're looking for a role, so I'd say stay out there. If you want to go back to uni and do more, then absolutely should. But I guess it's just get out there and be out there and take any opportunity that presents.
Yep. I've got to give a plug for the doing more uni. Surely. I recommend it, but I also just want to say that I think the pathway is sometimes easier than people think, and not as constraining. So sometimes people think it's going to be really hard, or I'm going to have a really hard time finding a topic, or when I finish, I'll be so specialized that nobody will want to employ me anywhere else. I guess I would say that doing more education, to my mind, shows that you're wanting to expand your horizons and your abilities, and almost kind of dials it up, right? It demonstrates that you're able to go away and investigate something and do something, so that if you want to come and work for us, we should be able to say, hey, look, go and investigate whatever it is. May not be in your particular topic area, but you should be having the skills to go and do that and present something coherent at the end of it.
Thanks for that. I've got another question here. So this is mostly for Janine. You mentioned that you were the only female in your graduating class, and the industry had a lot of work to do regarding diversity. Do you think the industry has changed since then, and will it continue to change or start to?
Yes, this is an interesting one. I think the industry's changed enormously. However, there are a number of people who wouldn't agree with that, who would say that it's actually been a glacial pace. But for someone who's been around for 30 years, it has changed enormously. So pretty much every mine site that I worked on in the first 15 years since graduation, I was the only female working in production roles. There were females in the office and in research and development, but it really has changed an enormous amount. And I think it goes far beyond just gender. Inclusion is about everybody having an equal opportunity to participate, and whether it's, diversity of thought, of experience, of ethnicity, you need a really well-rounded team to be a high-performing team. And I think the industry has definitely cottoned on to that now. And I think the main challenge now is making meaningful and sustainable change. And sometimes if you try and do that too quickly, you can have some unintended consequences. So I think we are making good progress, but there's certainly more we could do.
Yeah. I completely agree with what you said there, Janine. That's great advice. So I got a question from Alina. So this is for Janine again. So you've talked about the incorporation of social and environmental responsibility into the industry. Do you think there's a real push to minimize the social and environmental harm done by the minerals processing industry? Or are companies at the moment more geared towards making money and simply meeting standards? And do you think this is changing?
Now, I think companies are now being forced to take this seriously. So, the industry is highly reliant on investors. A lot of those investors will come from things like superannuation funds that are managed by bodies such as, the Church of England Pension Fund, who are absolutely cottoned on to the importance of social performance. So any company out there that's not taking this seriously won't be around for much longer. I can say that for sure. And it actually does make good commercial, financial sense as well to take this seriously. We are here to deliver value to the whole community, and the best way to do that is to look after the local stakeholders as well. So, without going into detail with the recent issues with Rio Tinto in the Pilbara, that has caused them enormous international damage to their reputation. So you can't afford to not take it seriously.
Yeah, that's a great point, especially with such a recent and topical situation. Emily has asked, it's mentioned that the mass digitalization of the industry is one of the major players in the present and the future. They've also heard that knowledge lives in the memories of people and not in a business. So how can you balance the push for growth through globalization and digitalization without inadvertently losing data and expertise?
Okay, I'd love to answer this one first. Capture the data properly. That's probably the first thing. You got to remember that people's memories fade, and people want to go on holidays, and people get sick, and people, do different things. So, yes, a lot of the memories reside in people, and that's how it has been. But if we record the data in a very structured way, what you'll do is you actually enable everyone in the future to learn from all of that information when they get to it. So a lot of mine sites in remote areas that we work with in the Congo and Zambia and across there, they have a lot of engineers that are transient. They're only there for 2 years and then they leave. So you really do need something in place to record the data so that people can look at it again later on, with their own eyes, rather than just accepting folklore as information. So I think the future is actually having data systems in place so that people don't have to remember everything, and that you can go back and review. Sometimes we don't make the right decision at the right time, but we can use the data to do that better next time.
I just want to add second the bit of the question about valuing people's experience and expertise. I think sometimes we do that too little. We tend to think that people who have been around a long time have forgotten how to run something, whereas actually they're the ones who often have a deeper insight into the quirks of the process, or what should really happen, or how you really do pull apart that pump, right? They actually understand those things better than others. And sometimes that's actually a really useful model of testing the output of the modeling work, right? Because sometimes people will do some weird things with computational models and result in something that might look fancy and colorful, but someone else looks at it and says, actually, no, if you turn the valve that way, if you increase the flow rate, you'll actually get the opposite result from what you want. And there's often experience has a deeper level of knowledge sometimes. So I value that as well.
Yeah, I think that's where it's so important to have the fundamentals, the fundamental knowledge when you're using a technology. If you can't interrogate what answer it spits out, then don't use the technology, because garbage in, garbage out, and you really need to know the theory behind it.
Thank you. I got another question from Thomas. So how much chemical engineering theory do you use in your role, theory and other skills?
I guess in my role, still a lot, although as the company's gotten bigger, I now have to do things like contracts and look at legal things and all sorts of other things. But I would say out of everyone that did my course at university, I'm probably still the most technical one as a percentage of time. So, I mean, I use it all the time. So, yeah.
Yeah, I guess my use of that would have varied over the years, but certainly I've always used it at some point in time. And whether it's been moving into a different environment, working in a laboratory with different unit processes, getting approached for a consulting role in, say, graphite, which I hadn't had experience in previously. So there's always opportunities to apply that basic chemical engineering, chemistry background.
Yeah, I guess for me, I'd say very little at the moment. So my role is mostly research management. What I do day to day is much more contracts and commercial and people and safety and so on. That said, the things you learn from ChemEng and things you learn from experience do come in useful all the way along. So if I'm visiting a lab to look at safety review and I'm looking through their work instructions for what they're doing or their activity risk assessment, then it's pretty useful to know the fundamentals of how things work behind that, even though I may not be applying it myself or doing my own flow calculations on my own. But it is something that is actually underpinning everything else I do.
It's great to see that you use so much of what you learn in university. It's not such a waste.
It's not a waste, but it's the start.
Okay, we got another question here. So outside of the normal vacation work, do you have any other suggestions of gaining valuable hands-on experience and improving your understanding of the industry?
Well, vacation work is as much as you can possibly get. So I took the opportunity at the end of first year, second year, and third year. So I probably did almost 12 months of vac work if I added it all up. And then you can often get a position, some intermediate work throughout your degree as well. So any opportunity, even if you can't get work itself, if you can go on a field trip or get on site somehow, every opportunity you can take, because you learn, theories, you learn how to learn at university, but hands-on is always the best.
Yeah, you can't learn everything from a book.
Mm.
But yeah, I would say, unfortunately, vacation work is the main mechanism, and do your best to get in there. We always have a paid internship here every year at our company, and effectively we do that because that opportunity was given to me when I was younger. Someone paid me to do an internship, and and I drove fire trucks and did all sorts of things. So it's important to know also, once you get into the industry, once you're in that position, to make sure that you make internships available for as many as you can, so that you can then pass that, pay that forward, so that everyone gets an opportunity.
Yeah, I guess I'd add that not everything is advertised. It's often by people who know people who find something. So talk with your lecturers about what opportunities they have, and I guess to come back to the point we started on, find something that you really like to do, and then find a way to do it. If you get paid for it, all the better. But if you don't, and you can support yourself, be a volunteer somewhere. Right? People will generally let you on site and give you a hammer, right, or something, a valve. Right?
Hopefully not.
That's right. Have a valve, pull it apart, clean it, and put it back together. Right, whatever it is.
Yeah, but it's I think unpaid internships are a bit of a cop out from the industry. I think you absolutely should be paying. I mean, you're not asking for full wages. It is only fair. So you've trained. Yes, you don't have a lot of skill, but you can add value.
I got another question here. So how does uranium mining fit into the metallurgy sector?
Oh, okay. I'll take this one. May I? Well, I mean, uranium is effectively an essential metal. We use that for all the nuclear reactors around the world. So if you think about decarbonisation of all our energy, you can't do that when you're burning anything carbon-based. So coal, natural gas, all of those options go out the door. The only way to decarbonize our industries and our planet is to actually use nuclear energy, and uranium is that. So in metallurgy, you dig it up and you refine it, usually as a concentrate, and then you send it to a converter that enriches the uranium from 0.7%, which is the background 235 levels, up to whatever is required for that particular reactor, which is usually 2-3% these days.
Yeah, I'll just add to that that you can be mining and processing uranium as the primary product, or it can be, for instance, a byproduct, as it is at Olympic Dam. Even though it's the largest single source of known uranium in the world, it is actually a byproduct of their processing. So in that sense, it's a really interesting series of processes to extract that uranium. So because they're producing copper and silver and gold as well. So there's some really great hydromet processes going on there, and leaching as well. And just to second what John said regarding the use of uranium for nuclear energy, of course we can't do that yet in Australia, but I've spent a lot of time in the uranium sector over the years, and it's also a byproduct in mineral sands where you have uranium and thorium. So I've done a lot of work around radiation safety as well. And we just came off a 2-week IChemE International Uranium Conference, which just finished last week, and was really tremendous to have people from all over the world in countries where nuclear power is their primary source of power, and just looking at what can be achieved. So let's keep the conversation going on that.
Yeah, I think it's while I'm a personal advocate of nuclear energy, and when I was chair of Engineers Australia's Chemical College, We advocated for it there as well. I think the political appetite is just not there. We'll continue to make our energy from other sources, and we'll continue to power our submarines using diesel and batteries.
Are you trying to antagonize me?
Yeah, don't get us started.
I walked through the sub last year. It was good fun, but it's a giant battery.
I got a question here from Gav. So, do you think that your roles in metallurgy and minerals processing have coincided with other specializations in engineering? How do you think that we as chemical engineers can stand out?
Well, I guess as chemical engineers, we're we're probably the smartest of all of them and probably the wittiest as well. So, so we tend to stand out anyway. Sorry, I make fun, but I think as an engineer, you're they're all just different flavors of the same thing. For example, an electrical engineer gets flow when the switch is closed. We get flow as an engineer when the valve is open. Interchange a little bit of the terminology, and it's much the same thing. And you can move around within engineering. That would be my.
I think engineers are critical to the whole thing. I think we are the system integrators. Right? We have the big picture view. You have enough of the fundamental physics and chemistry that you know how that works, and enough of the big picture mass and velocity and so on that you can put them together. But that point is actually, I think, part of the future trend is that connectedness with other skills and abilities, and knowing how to tap into what you need when you need it. Right? So being able to talk the language of electrical engineers, like John just said, or being able to talk to a mechanical engineer about the bending modulus on such and such, right, is actually really, really useful, as is the language of commerce and intellectual property and safety. You need to have all those skills.
Yeah, I think the further you go through your career, the less important the title is. So it doesn't really matter whether you studied engineering or applied science or whatever it might be. I think they really do start to merge into each other, and you've got civil engineers who might be crossing over into tailings design. You've got geotechnical engineers who might be doing mechanical engineering. There's really a lot of, I think, similarities between them, and you can definitely broaden your horizons as you go.
It's great to hear that we're not all alone.
No.
Got a question from Matthew. So he's curious to hear your thoughts on transitioning between different metals within your career and moving from site-based work to an urban consultancy type of work. He wants to know if this is largely just a facet of networking and applying for those roles, or are there any other suggestions that you have to enable this?
I take it that's for me, Jack?
I think it's for all of you.
Right.
Go for it.
For myself, so I started out in base metals, so lead zinc, and then moved into industrial minerals, mineral sands, so rutile, zircon, ilmenite, essentially for titanium at the end of the day. And so they were really my main specialties, although I'd worked in nickel, a little bit in iron ore as well. Really, when I took up the role at Amdel, I became, I guess, into a lot of other commodities at that point. So uranium, a whole bucket load actually. So that was really quite interesting, and I think that then gave me the ability as a consultant to be quite well-rounded, because it does take a leap to go out and start your own business, and the work won't come to you unless you've built your networks and people, can vouch for you and actually, get a foot in the door, so to speak. So I think if you're going to go into consultancy, you've got to have a good, solid experience in industry with plenty of contacts.
Yep, I'd agree with that entirely. So, I mean, within CSIRO, we have a research consulting kind of stream. You can be a research consultant, and it's very much about how you build those networks and how you. I mean, this is both Janine's and John's points during their talks of how you deliver on what you've said you're going to deliver. Right, your track record stands a great deal for you. And it's those connections where you've helped someone, you've been clear about what's needed, you've delivered it, and that's what builds, really. And you can't go past that.
That's great. So we've got a question from Thomas again. So how can or will the metallurgy industry support renewable and alternative energies?
Well, that's easy. We make everything that goes into it.
Exactly.
And absolutely, renewable is something we should continue to evolve and develop and make sure we get there. But these things take time. It's as simple as that. One day we might be able to live off of it, and that would be wonderful if we could do everything with solar and batteries. Just if you think of the scale of the problem, that's where it starts to fall over a bit. So I think we have a lot of work to do still, but metallurgy supplies everything you need to make those things. So yeah, I'd say fundamentally it does that.
Yeah.
I'll go a step beyond that. I think there's opportunity for chemical engineers to think about the new economy in a smarter way, that is using the energy in a more efficient, further upstream way, right? Things like not just turning solar power into electricity, but actually concentrated solar thermal for doing the metal reduction itself, right? You actually cut a step by being smarter about how you design your process to input different energy sources into it. Okay. Same thing goes for hydrogen, right? If we're going to move to a hydrogen economy, don't just use hydrogen to make electricity. Let's actually work out how to use hydrogen in chemical processes much more intelligently.
Thanks for your answers. So we've got another question. So you all mentioned how Australia can be very conservative with trying new technologies, or sort of a paralysis by analysis. How would you recommend balancing between moving forwards with new technologies and trying new things that might be more efficient, and the aversion to like risk in a safety or technical sense?
I think that the answer was already in Leon's presentation, R&D. If you're doing the work, you can validate these things and to prove the technology works. It's not really even paralysis by analysis. I think it's paralysis by, I guess you can't be blamed for doing something wrong if you don't do anything. And that's typically what you see.
Yeah, and I think also sometimes we bed ourselves up a little bit on this. We say, oh, Australians are very conservative. Well, there's actually been some incredible technologies that have come out of Australia in terms of the mining sector. So, some of them are software related, but, things like the, various mining softwares that we use, whether it's groups like RME who do the robotic mill relining. You've got the Xstrata work with, got Jamison cells, you've got Isosmelt, and, there are a lot of technologies that have come out of Australia as well.
Yeah, I was just going to add that it is a tough world, right? When someone's trying to do, even from an economic point of view, right? You have kind of the stage gates of how sure you can be of your final economic answer, right? And at R&D level, at technology readiness level of 3 to 5, you're doing your techno-economics on your plant, you're plus or minus 50, right? Who's going to take the risk of funding the next level of development when you're plus or minus 50, right? And then you get to running a pilot plant, and your full-scale economics are still plus or minus 25, right? Is that too much risk for someone to take? Often in the world these days it is, unless you're really, really radical on the upside of what your process can do. Someone's got to take the risk. Someone's got to drive it. It takes courage to invest in that.
It looks like we've gotten through all of our questions. So are there any topics that any of you would like to talk about while we have a few minutes left of the panel, maybe about the trends for the future of metallurgy?
I would say that, the industry is always evolving, and the use of lots of different technologies is increasing. I'd say, as we've said before, getting more for less is probably a thing, and I like the whole, let's, as Australia, let's reduce the valency of all our exports. This is it's a constant nuisance to me. It's like, why are we shipping all these effectively raw products out when we could be manufacturing them here, refining them here, and actually making things? We have a highly skilled and educated workforce. To me, it just seems like energy costs seem to be what hold us back. So I'm hoping Australia can move in that direction more, because we have a wonderful resource here. So we should be shipping out final products, i.e. cars and batteries and everything else.
Yeah. I completely agree with that, John. There are so many opportunities that we let pass us by not taking the next step with advanced processing or enrichment or whatever it might be. I see us definitely needing to be a lot more active in that space. And I think the current pandemic has also exposed a number of limitations when it comes to our supply chains as well. And I mean, if there's ever been a demonstration of how important it is to have your own manufacturing industry, this has definitely demonstrated that for sure. And, it's actually quite, I feel personally unethical for us to be sending our uranium to other parts of the world and not taking the final waste product back for disposal when we know we can do it really safely in this country. So, I guess just in terms of the energy thing as well, something that's really important in mineral processing is comminution. So, size reduction and liberation of minerals, and that's really the most energy hungry part of the process. So anything we can do to reduce that energy required there, and there are things, a lot of other things you can do, like pre-concentration, to actually reject waste up front and limit the amount of material you need to process. So lots of smarter ways we can look at what we do.
Yeah, like even nuclear fuel leasing. That's
Yeah.
I just want to make the case for the recycling side of things as well, because we overlook that, frankly, to our peril. And often the resources are there take copper, for example. The grade of copper that you dig up now to make copper is a lower grade than you'll find in your desktop computer, right? So the e-waste that we throw out, that we typically ship overseas, actually has more of those valuable elements in it than the very rocks in the ground. And the issue is the process technologies to actually extract those metals, right? It's a real critical issue. And it can be pyrometallurgical. You can chuck batteries into a giant furnace like they do in Belgium, right? That's one option, right? Or you can keep working on smarter ways to dismantle that, to design it for end of life, to think about how you can extract your different parts into valuable products. It's a real chemical engineering, metallurgical point of view that I think is going to shape the future of this nation.
Those are some really great points about the future of the industry. I think if we don't have any questions, we might be able to wrap this Q&A up for just a little bit. Thank you so much for taking the time to present to us and for being a member of this panel. I can speak for myself and probably everyone who's come here we really appreciate that, for you coming here and spreading your knowledge. So for all the students attending, for the rest of the week, tomorrow we have a couple of streams. We've got one on sustainable design. This is mostly about human-centered design, systems engineering, and how that ties into chemical engineering. And we've also got one on alternative energies. So we've got a few professors at various universities, and they're going to present some of the research that they're doing with biofuels, hydrogen energy, and converting from that energy into actual electricity, and how that can be optimized. Also, please keep in mind, tomorrow after the talks, we have a trivia night for students. Maybe a pretty laid-back way to get to know each other. And on Friday, after our talks, we have a networking session. So all of our industry people, including our three lovely presenters, are welcome to attend this networking event, which will be on from about, it looks like 4 o'clock Central Standard Time, so that would be 4:30, I think, AEST. And on Thursday, we'll have 2 streams about biotechnology and pharmaceutical engineering. So we've got one about the pandemic's response from the pharmaceutical industry, and another one about some of the research that's going into biotechnology, pharmaceutical reactors, and the like. And then Friday, we will finish off the summit with some talks about the future. We'll have Alexandra Meldrum and Tim Hoskin talking about where they feel the future will be heading in the next 5 to 10 years of the industries that they have been a part of, which is quite multiple. So thank you very much for everyone attending this stream and for taking the time out of your day to, get some knowledge and learn a little bit more about the industries. And thank you again, presenters, paying it forward and giving some knowledge to some students and young professionals. And hopefully these students, when you move forwards, you can also pay it forward when you're in the roles of Leon, Janine, and John.
Fantastic. Thanks very much for the
Thanks, everybody.
Bye.
Bye.